Okay, there we go. All right, so when we finished last time, we were doing the graphs of linear, they called them functions, but I had told you equations, right? And we stopped with doing X intercepts, Y intercepts, slope. And that was the last topic on the test. And now we're going to return to that, but now we're going to start doing some applications. So word problems. Applications of linear functions, which again, I'm scrapping that word and I'm using equations. So the key to this is that we're going to try and take some word problems that are probably not very realistic. Most of our word problems haven't been very realistic, right? But the whole idea is that you have some situation in the real world that you're going to try and model with a linear equation. And then we can do all the stuff we've done with a linear equation. Find the x-intercepts, y-intercepts, slope, all that. And that now it's going to have meaning to us. So let's just take a look at, I'm going to look at number 1 here. It's about Mr. Thompson is on a diet. All right? Mr. Thompson currently weighs 260 pounds. He loses 4 pounds per month. £4 a month. Write a linear model that represents Mr. Thompson's weight after M months. So the idea is this. You want to come up with some equation that's going to model what's happening to his weight. Right? So it's going to be your x and y axes, but we're only going to be looking at the right side of it because this right here, instead of using the variable x, we're going to use variable m because it says m months in there. And this is going to be the number of months. And then the y-axis is now going to be what? His weight, right? So, and it's measured in what? Pounds. So the question is, how much would he weigh at 0 months? 260, right? So I could come up here and I could mark out here 260, and I know that that point represents where he started, what his weight was when he started. And then every month, right, after 1 month, it's going to drop down to what? To what? He's losing 4 pounds a month, so 256 after 1 month? So he'd be down here, let's say this is like 256 right here. And then after the second month, he loses another 4 pounds, right? So he would be at what? 252. And what we have here is the assumption that the weight loss is linear, meaning every month it's always 4 pounds, 4 pounds, 4 pounds, 4 pounds, right? The assumption here is that we are going to model this using a line. So we could connect these together, and eventually, if he does this long enough, according to our model, eventually he will no longer exist, right? But that's why a linear model is not a good model for weight loss, but it's a starting point, right? We can get a basic idea of what's going on. Okay, so what we want is a linear equation that models this. So you can see the line. What do we already know? What is this on if we were to imagine that our line went forever in each direction, what is this point on a line? Our y-intercept, isn't it? So in terms of an equation, we know what the y-intercept is. Let me try and come up. So we want an equation. I should put here linear. Relating his weight, which we will call W, to the number of months, which we will call M. So his weight should be equal to what? 260 is what he starts at. And then what? Minus 4M. So what we're going to do is we're going to take away 4 for every month. So isn't the negative 4 this slope? Down 4 over 1. Down 4 over 1. Down 4 over 1. Down 4 over 1. Now it's not drawn to scale. Do y'all know what I mean by that? Like 1 unit this way is not equal to 1 unit that way. That's okay. We do that a lot just to make it all fit on one picture. Or to fit easily onto our paper. So this slope is equal to negative 4. And the y-intercept is 260. So you can write it this way, or you can write it more like we did with our y equals mx plus b. That would look like more like y equals mx plus b, doesn't it? Y is the w, equals m negative 4 times x, but x is m, plus 260. Good? No questions? Okay, that's our model. This is our model right here. Now let's look at part B. After how many months will Mr. Thompson reach his goal weight of 220 pounds? After how many months? So how many months until Mr. T is how much? 220? Well, we have our model, right? We have our model here. We're looking for months, right? The time measured in months. That's what we want to know. And we want to know what that value is, which makes his weight what? 220. So all I have to do is use this equation right now, replace W with 220, and then write the equation. So 220 equals negative 4m plus 260. Now you probably could have counted, like minus 4, and counted how many months, but this is a more efficient way because we can do this for any weight. And so solve this linear equation. We're trying to solve an equation. There's only one variable in it. Isolate the variable, right? So start moving things around. How about subtracting 260 from both sides? Sound good to you? Yes? So subtract 260. This will give me negative 40 equals negative 4m. And divide both sides by negative 4 and we have 10. Does everyone understand the importance of doing this? And that, like on a test or on a problem that's maybe not so clear, it's obvious he lost 40 pounds, right? 4 months a pound, or 4 pounds a month, 10 months. We could probably do that mentally, but we need a way that we can do it if it's not so easy. Agreed? Okay. I should have, I probably have it on my laptop, but I don't think I'll show it. Every once in a while, I'll like train for a triathlon or something, and I always have to drop weight for it. And this is exactly what I do. I have a model of a linear model that I use to figure out how long it's going to take me to get to my like competing weight. And so I can tell you right now that when I train really hard, my slope, my M here is about negative 0.321. I know that seems crazy, but that's per week. So I lose about a third of, no, hold on. That's a day, sorry. So when I'm really training hard, I can drop a third of a pound a day, about, and still stay healthy and not, go crazy, not die, exactly. But that's like the max of what you should ever do. You should never try and drop weight any faster than that. But Per day, yeah, like a third of a pound a day. Yeah. But then I plateau out, you know, I get to a point where, yeah, I don't just wither away into nothing. So, all right, well, how about a bacteria problem? A bacteria population doubles every minute. Doubles every minute. Explain why this population growth cannot be modeled using a linear equation. Why it cannot. Okay. What's that?
I mean, well, it won't make a line.
It won't make a line. So let's see why it won't make a line. All right, let's see. If you let's start with one bacteria. Okay, let's say here's one bacteria. I'm even going to put a little smiley face on him because he's a happy bacteria. All right, there he is. You start with one. After 1 minute, okay? After 1 minute, how many are there? It's doubled, right? I'm going to stop drawing the smiley faces. Okay, so this is 0 minutes. I'm going to make almost like a little table here. This is 1 minute. Okay, how many should be there after 2 minutes? 4. But what's happening here is that one's split into 2, right? And now the next one's going to split into 2. This one's also going to split into 2, so you're going to have 4 after 2 minutes, right? So if I were drawing this right now, okay, if I were to draw this and this were minutes and this were the number of bacteria, look at what this picture looks like. At 0 minutes, how many do we have? 1. After 1 minute, how many do we have? 2. After 2 minutes, we have 4. Y'all okay with that? Does that look like a line? I'm a little off here. Does that look like a straight line to you? Let's try the next one. How many would I have after 3 minutes? Careful here. How many? 8. Not 6, right? We have 2 from here, 2 from here, 2 from here. See, each bacteria doubles after 1 minute. So now you're going to have 8 of these guys. So if I come out here to 3, I'm way up here at 8, right? And do you all see that that's not a line? I mean, can you tell that I can't connect these with the straight line? And so this is not linear growth. This is what we call exponential growth. So the whole point of this problem is just to let you know that not everything can be modeled with a line. Bacterial growth is one example. All right, let's do another one. Tuition. Let's do tuition at college. So there's a college called XYZ, and it is $100 per credit hour. And an additional $75 student fee. It's a pretty cheap college. Can we model this with a linear equation? Well, let me finish this. What is the one-time charge or fixed cost? So the student fee, right? No matter what, if you take 12 hours, 9 hours, 6 hours, doesn't matter, you have to pay the $75 student fee. So our fixed cost is $75. All right, the next question. What is his variable cost? Who's his? I don't see any reference to a guy anywhere. Okay, what is the variable cost? So what matters? What's affecting the cost of tuition? I mean, what changes? What's variable here? Yeah, how many credit hours, right? So the variable cost is the credit hour cost, right? And then write a function t of x. So this is the first time we've seen this notation before. The tuition, and then parentheses x. What this is saying is we are going to say that the tuition depends on x, is a function of x. And x is going to be the credit hours. Let's not do cost. Let's just call this credit hours, x. That changes, right? How many hours you take? So tell me about this cost. Definitely, no matter what, it has to be what? If you're going to go to school there, no matter how many hours, got your fixed, right? 75? Plus, because you have to pay something in addition to that, what? $100 per credit hour, and if x is the number of credit hours you're going to take, then it's going to be 100x. So if you take 1 credit hour, you're going to pay $175, right? 2 credit hours, 200 plus 75, 275. And that is a linear equation. Now, if we scrap this little notation here, we could just write, tuition equals 75 plus 100x, and it would be the same thing. We would have x being here, we would have t being here, and then we'd graph our line. What would the y-intercept of that line be? 75. And we'd have a slope of 100, right? So it'd be a positive slope, not the guy losing weight, right? It would be this. So the more credit hours you take, the more expensive it's going to be. Okay. Let's move on to I think 5 looks pretty good. Does everyone who has their stuff with them on number 5 have Joe and a part-time job walking a dog? Okay. Okay, so I'm looking at the one that's Joe has a part-time job caring for and walking dogs. All right. Someone's got to do it, I guess. He estimates his annual insurance and costs at $420. Annual costs at $420. What is that looking like it's going to be in the problem? Like, compared to the last problem, what is that kind of going to be like? The fixed cost, right? The $75 student fee? Like every year he's going to have to do that. Like for whatever reason, he's going to have to pay $420. On average, he spends $4.50 on gasoline per visit. I guess a visit meaning he's going to go take care of a dog or some dogs. He charges $15 per visit. It says, note that this is an annual cost function. Part A, what is the one-time annual charge or fixed cost? We already said, right? The $420? B, what is his variable cost? These both, right? These are both part of the variable cost. Because every visit he makes, he's going to pay so much in gas, and every visit he makes, he's going to have a charge, right? But these work against each other, right? Like this is income, this is out, right? So let's actually label this thing as a variable. Can we call it, I think they want us to use x. X is going to be the number of visits. Isn't that the thing that's going to control his cost? How many visits he actually makes is going to be the variable here. And then finally, we can write a cost function. And they want you to write it C of x. Let's see if we can do it. What's the fixed cost? 420, so we can put that out here. Plus, now, how do you want to do this? You can do this different ways, but let's see how, anyone have an idea of how they want to incorporate?
Minus 4.5x?
15x, so 15x, you want me to put plus 15x, because that's going to be money coming in, coming out. See, we have to be a little careful here. We want this to be a cost function, right? Cost. How much cost does he have? So is this 420 income or out? Expense or it's out, right? No matter what, he's in the hole 420 per year. So we should incorporate this 420 in our equation as a negative because it's a cost, right? So let's go negative here, 420. And then the 15 is income or expense? It's income, right? Money coming in, so it's a plus. And then what about the 450 in gas? It's going out, so minus 450 per visit, so times X. And now we can actually put these together, right? Because they're like terms. So what's 15x take away 450x? What is it? Plus 1050x. Does that look like a linear equation? Does that look like your y equals mx plus b? Yeah? If I graphed it, the y-intercept is what? Negative 420. And then your slope is positive, isn't it? 1050? So it's going to go up like this. Agreed? What is the importance of this point right there? What is the importance of that point? That's actually called the break-even point. It is the break-even point. So if he's going to run his business, he's going to be out 420 no matter what. So he's got to do some work or else he's out, right? How much work does he have to do just to break even, just to offset the 420? Well, that's going to be, right, this is X. This X intercept tells you where his cost is 0. Where is that? So this is your cost, right? If I were to say C equals 10.50x minus 420 like that, if I were to ask you to find where he breaks even, I'm asking you for the x-intercept, right? So to find x-intercepts, you set y to 0, but we don't have y, right? We have c instead. So all I'd have to do is set c equal to 0. I realize this question I'm asking you is not in here, but I'm just trying to see if you can make the connection. If you set c to 0, then you get this. If c equals 0, turns into 0 equals 1050x minus 420. You move the 420 to the other side, and you divide now by 1050. So someone please on their calculator.
840?
What is it, 840? So how do I interpret that? This is my little dog walking business. I'm going to have to do how many visits to break even?
That's 40.
Oh,
Sorry.
it's 40. Okay. Yeah, that seemed a little off. 40 even? Oh, okay. Well, going to have to do 40 visits, 40 dog walks a year. It's 52 weeks in a year, 1 a week. I don't know how busy this guy is, so maybe it works out for him. Okay. Do you think you can handle some of this? You're going to have to just go through the homework on your own and see how the problems look. Okay, let's talk about a different type of problem. These are called mixture problems. So we're stepping away from that for a minute. All right, I'm going to look at number 1. If there is a mixture of 7 liters of water and 17 milliliters of ink, write in decimal form how many total liters there are of this mixture. How many total liters? So what do you have to do? Convert what? Milliliters to liters, right? Let's convert this milliliters to liters. Because what we're doing is we're taking 7 liters of water, we're adding 17 milliliters of ink, and we're mixing it up, right? And we have some ink solution there. How many liters are there? So first, 17 milliliters, we did this on the test, over 1. What's the conversion to go from milliliters to liters? Give me any relationship between them. 1,000 milliliters equals 1 liter, right? That's our relationship. So I'm going to use this equation. I'm going to write my fraction out here. What goes on top? Liters, 1 liter. Bottom, 1,000 milliliters, right? So this turns into what? .017 liters. That's how much ink you have, right? Add it to the water. Yeah? So your mixture is the 7 liters plus the .017 liters, which of course is just 7.017 liters. Okay, let's do number 2 here. If there is a mixture of 2 liters, did anyone have a question on that? All right. If there is a mixture of 2 liters of 10% butterfat milk, okay, and 1 liter of 0% butterfat milk, also called skim. How many liters, and we're going to mix these together, okay? We're going to take these two, we're going to mix them together. The question is, how many liters result, and what is the percentage of butterfat in that mix? There's all sorts of different ways to do this. All right, so let's see if we can come up with a way that makes most sense. Two liters, right? It's 10% butterfat milk. That means 10% of it is butterfat, I guess? Yes? So how much of this is butterfat? Only 10%, which is a small amount, let's say. If we were able to separate the butterfat from everything else, 10% of it would be butterfat, the rest would be the rest, right? So how much is that in there? How many liters of it? What's the computation you have to do to figure that out? What's that? Yeah, convert this to a decimal, 0.1, right? 0.10 times 2. So you're saying 10% of 2 liters is what? 0.2. So this is 0.2 liters of butterfat. I'm just going to put butterfat, right? Does that make sense to you all? If you got 2 liters of stuff and they're saying 10% of it is butterfat, then that means 0.2 liters of it must be the butterfat. The rest of it is just water or whatever else. We're going to take that and we're going to mix it together with another mixture over here that's just 1 liter, and it has how much butterfat in it? 0 butterfat. When I mix those together, how much do I have total? How many liters will I have total? 3 liters, right? I'm going to have 3 liters. So I mix them together now. I have 3 liters now. How much of it is butterfat? Still 0.2, right? We still have down here, that 0.2 had to come with me, so we still have down here 0.2 liters. So the question being asked here, there's 2 questions. How many liters result? So what's the answer to that question? 3 liters, we're done. What is the percentage of butterfat though? What's the percentage? It was 10% here, right? But here, the question you're asking is 0.2 liters is what percent of 3 liters? 0.2 liters is what percent of 3 liters? And you convert that into an equation, which would be 0.2 is equals what percent is X times 3. That's what I asked you to do on the last test, right? Something like that. And we're solving for X. All you do is divide both sides by 3. What do you get? 0.06. Close enough? 0.666? Ooh. Okay, repeating equals X, which means, convert that to a percentage, 2 places to the right, 6.6 percent, right? Approximately 6.6%. I want you to try the next one. I'll put it up here on the board and give you a little bit of time. You have a mixture is 2 liters of 11% saline, which is salt, and 3 liters 3.1 liters of water. Mix them together, okay? Mix them. First question, how many liters? Result. What is salinity? Percentage. How much salt is there as a percentage? If you have it, raise your hand. If you have both of them. Okay. Let me see what you're getting over here, Sean. So 5.1, and then you divided. So where was, did you do this and this together? Right? Question, you got to figure out how much salt is there to start. This is just like the problem we did before. So 0.22 liters. So there it is. What are you doing here? I'm trying to. Okay, that I got you. And then you divide through. Okay, got you. Whenever you're working with an equation like that, you just like work straight down. Because if you look at it this way, you're saying that this equals this. Okay, but you got it. Anyone else getting it? Yeah? What are you getting for your salinity percentage? Around what? 4.3? Oh, 4.3. I think, how many liters did you have total? I think you didn't take that into account. When you put these together, it's 5.1. Not 3.1. Yeah, sorry, I didn't catch that the first time. 0.43. Then convert that to a percentage. 4.3. It's looking like 4.3%. Did you get 4.3?
I calculated it out. I know what I have to do. I just don't have my calculator out. It's just 2.22 divided by 5.1.
Yes. Okay. All right. So how are you doing here? Okay, good. You get your amount of salt, and you're going to get this result. Yep. And then you take that and set up your equation. It should be this number divided by that. Okay. Did y'all get it? So how much salt was there? To start, how much salt was in here? Okay, it's 11% of 2. So you have to do 0.11 times 2 first. That's how much salt is there to start. Are you following that, or? And then you take that and divide it by the 5.1 that you get when you mix them. You got 4.3-ish percent? Okay. Yes, no, yes? 5.1, yeah. Because you're adding the two together. So now you have 5.1 liters, not 3. Did you round? Let me see what you're... Did you do 0.22 divided by 5.1?
Oh, that's what I forgot. The 0.1.
0.1, there you go. Okay, I think mostly everyone is there, can probably finish it off. Look, the theme of the two problems I just showed you is that you have a certain container with a certain amount of stuff in it, salt, butterfat, milk, and you're going to mix it with some other container that has however much of it is. It's been 0 the last 2 times, right? It's nothing in here. You want to mix them together. When you add these two together, you're going to get a total container now. It's going to be those two amounts added together, right? So 2 and 3.1 is 5.1. But the question is, how much of it is still the salt or the buttermilk? Well, you have to figure out how many liters that is. How many liters of this salt there is. And to do that, don't forget the step. You have to take 11% of 2 to figure out how many liters there are. You can't say 0.11 liters. That's not how much there is. It's 0.11 times 2. If this was, 15, then it would be 0.11 times 15. That's how much salt is there. Now, the reason why it's important for us to understand this is because of the next question. All right. I'm going to look at number 5. It's saying something like, how much water is required to be added to 1 quart of 3% milk to result in a 2% solution? So this is very different than what we just did. All right, I've got some milk. All right, I've got 1 quart of 3% milk. Now let me draw a picture of what this means. I've got 1 quart and 3% of it is milk. So if I could, it's water and milk mixed together, all right? So if I look at it, it's actually only part of it is milk, right? 3% of this is milk. How many quarts of milk are in there then? How many quarts of milk? I have 1 quart of everything. How many quarts of milk are in here? You're going 0.03 times 1 quart, right? Understand that? So you do 0.03 times 1 quart, and that tells you you have 0.03 quarts of milk. Okay, so that's what I'm starting with. I've got this 1 quart of 3% milk. They want me to come over here and mix that with something else, right? With water. And at the end, I want to have a 2% milk solution. How much water do I pour in? Mix with it. Do y'all see the difference between that and the previous one? The previous one, they told you, hey, take these two and mix them. What's the result? Now they're telling us, take this one, mix it with water, and they're telling us about what they want the result to be. So I'm supposed to come in here and add something to this, right? I have some container here of water, which means you have how much milk? 0% milk. And I don't know how much there is of this. I don't know how many quarts there are. I don't know. That's the question. I need to add those two together. And what do I want my result to be? Just 2% milk. This is tricky. It's a lot different than the last one, right? So when I add those together, I'm going to get a result, and let me put my result over here. The result of adding these two together should be some mixture, and it's 2% milk. Okay. Everyone understand the problem? Yes? No? What do they want? What are they asking for? They want that, yes, but what is it you have to actually solve for? How much water you're going to mix with this, right? That's the question. How much water do I have to mix with this to get a 2% solution out? So I'm going to write that down. How much water in quarts? Why am I in quarts? Well, because that's what they started with, right? Quarts. Do I need to get a 2% milk mixture? Well, since we want to know how much water, why don't we call this thing something? And we don't know what it is, so why don't we use a variable? X, W for water, it doesn't matter. But we've used X a lot, right? So how about X? We're going to call this X. So I'm going to come in here with this 3% milk solution, 1 quart of it. I'm going to put it in this big old bucket, all right? Then I'm going to come and I'm going to pour in how much? I'm going to pour in X and mix those up, and at the end I need 2%, right? Okay, we're kind of reversing what we just did. So if I were to actually ask you right now how many quarts of water you're going to add, you would tell me what? X quarts, right? X quarts? X quarts of water? Agreed? How many total quarts are you going to have when you add these two together? Whatever X is plus 1. Agreed? So your mixture, I'm running out of room here. I'll leave this. This was 0.03 quarts of milk. Okay, when I add them, the mixture, I will have X plus 1 quarts. Yes? how much milk will be in there?